So we're gonna move on to Shanqi's talk, fellow co-chair. So if you would like to share your screen. All right, and then I will change over to the timer, and you can go ahead whenever you are ready.
Hi, this is Hsiang, and I hope you can see and hear the presentation well. That I'm presenting a recent modeling work by me, Xu Wang, Anthony Carell, Noah Hood, and Mihai Horani about the grain size evolution of on asteroids. And the main motivation, as some of you have seen previous version of this presentation, is that the motivation is we try to understand what causes the diversity of these different sceneries on these bodies. As you can see on the moon, we have very dusty surfaces, and moving to smaller bodies of like the Bennu and Ryugu, which recently explored by these excellent sample return missions. And these worlds are tiny and dominated by, and the surface is dominated by boulder fields. And that's why we are thinking in the way like how this is, what are the processes shaping the surface.
Oh, you're muted, Sean.
Oh, here we go. Sorry. Yeah, I just muted myself. And the way of thinking, of course, we can follow an analog we have on Earth. That along the shoreline, the conditions could be different just from the very short different distances. That depends on the in situ conditions that we could consider very different process that will determine how the shoreline will look like. For example, we could have transportation processes that, for example, bring the sand from these rocky shores and deposit it into the more stable regions and from the beach. We can also consider the fragmentation process that bring down and change the size distribution. And so for asteroids, we consider three processes to be the key players. On the starting from the left, we have thermal fragmentations, which has been simulated in the lab and also observed on Ryugu and Bennu, that this could be a major fragmentation or process that break down the border into smaller pieces. And we can also have, of course, impact processes that produce fragments, and depends on the escape speed of the body, how much it can retain its materials, and we can have a removal process that, in contrast to a thermal fragmentation, it will remove material likely smaller pieces from these airless bodies. And lastly, we also consider electrostatic dust transport process, which is modeled in the lab, as you can see, by shining electrons and UV lights. These ionizing radiation will produce a different charge on the porous regulars and allow charge to accumulate and repel when sufficient to repel each other and produce this transportation kind of hopping motion of particles with a speed roughly lower than a meter per second. And some of you might hopefully remember what we presented last year is that because of the small gravity of small bodies, that we show that for asteroid at 1 AU or nearest asteroids at 1 AU heliocentric distance, that below 1 kilometer of the radius, they don't have gravity enough to retain materials losing by electrostatic lofting. And so for that, we predict that smaller bodies will be basically fine-grained material free, and that is consistent with what we see. And the progress we made this year is that we also we not just derive compare the rate of fine-grained material production, but we also expand to model the size distribution of the system, of the regular system on asteroids. And the same, we consider these three different processes working together that shape the size distribution of asteroid regulars. And of course, on the left, you have thermal fragmentations that basically doesn't change the system mass, but bring down masses from larger particles into smaller particles. And of course, we have impacts that produce fragments, and depends on the gravity. For small bodies, most of the ejecta can escape. And we also have the electrostatic dust lofting that basically only operate in the mass budget terms that only affect the smallest particles, which of course depends on the size of the body, on the extent of these effects. And putting all these together, we have this very busy time evolution. On the top, you have the size and the surface area distribution of the regolith on these 500-meter radius hypothetical asteroid located at 1 AU. And we start with a rather steep size distribution of with an index of -3.5. So at the beginning, actually most of the surface, about 90% of the surface, is covered by grains smaller than 100 micron. But with time, and because of this prevalence of small particles, electrostatic lofting is the most important process at the beginning. As you show from the bottom plot, shows the rate of various process. And you can see in the first few thousand years, electrostatic lofting remove a lot of fine-grained materials and start to shaping the size distribution, at least in the grain size below 22 microns, which is the range can be affected by electrostatic lofting on a 500-meter body. But with time, with the losing of fine-grained materials, you lose the protection of these material to the larger grains. So they are more and more exposed to space elements, and their erosion start to pump up, and you can see the fragmentation rate start to increase a little bit, experiencing a bump, kind of a minor increase after 10,000 years. And that's because the more exposure of these larger grain populations, and the more effective they are being eroded. And therefore, by introducing to the electrostatic forces, you not just change the smallest population, but you introduce this coupled size distribution evolution. And if we want to bring up the contrast that this is on the right, shows the case for much larger objects with a 5-kilometer radii. And you can see that the electrostatic forces only affect, only be able to remove particles 2 micron or smaller. And that means electrostatic lofting is actually a minor process here, and the dominant process is fragmentation. And you can see after 10 million years, more than 50% of the surface is covered by micron-sized grains, in contrast to the small ones, where after the simulation of the same period of time, that 50% of the surface should be covered by grains larger than millimeter. And we can also simulate a lot of different cases, basically using a Monte Carlo approach to sample the different combination of the initial parameters as shown here. And we see that at different, for grain, for parent body or asteroid size radii from 100 meters to 10 kilometers, it's basically a linear relationship between the time where the fine-grained material is depleted, which is defined by that more than 50% of the surface area is covered by grains 500 micron or larger in radii. Or in another way is that these smaller grains cannot form a uniform, if they distribute uniformly, cannot form a monolayer covering larger grains populations. And so it seems that these processes are actually quite effective based on the parameters we considered, and small asteroids, as you can see on the left upper part plot, that asteroids smaller than 1 kilometer are more likely, more than 50%, to form to be depleted in fine-grained regolith. And this is the summary slide that basically we consider 3 processes as discussed, and the key or the kind of the new elements is the electrostatic lofting that removes small particles and only effective on very small bodies. And the size distribution we derive is roughly consistent with the in situ measurements reported from OSIRIS-REx and Hayabusa 2 missions. And also what I want to stress is that by losing fine-grained material, it also changes the thermal properties of the surface, which could mean that it has implication to the orbital evolution or the surface spectra characteristics for small asteroids. And thank you for your attention, and I take questions.
All right, thank you so much, Sean.